See if we can get our microphone attached here properly. So we wanted to do a little follow-up video talking about some expanded use cases. One of the things that we've been doing in the CNC world for a century is actually milling. In other words, cutting a pocket in a piece of material so that we can create a joint or we can do inlays and other kinds of things like that. In the laser community, there's not a lot of examples of that. And one of the things that we thought we'd look at is, what can I do with an old RV door? Now, if we look at the RV door, this door is made out of, I think, oak. It's severely cut from 30 years of being in an RV, bounced all over the place. And the question was, well, what useful purpose can one take a piece of material like that and use for it? And so what I've been exploring is I wanted to figure out how to make a pocket, because I can make a plaque out of this. I can put mirror or any other material or multiple layers of wood materials and so forth, and create various art and products. But I needed to sit down and figure out, well, what is it going to take? And do I need to use a drill in my router? Or can I make the laser do some of the work? And then the other thing I looked at was, how many passes does it take to get how much depth? And what can I do in a 35-watt laser versus a 70-watt laser? In this particular case, I'm using an Atom Stack X70. And one of the comparisons we're looking at between the 35-watt mode and the 70 mode is the fact that, do I get a more accurate cut when I use half the beam width? Because the difference between the modes is not only power, but there are a row of a column of 7 diodes in 2 rows. And so basically in 35-watt mode, you're turning 7 diodes off. So now you have a beam that's exactly 1/2 of what you have when you have 70 on. So we wanted to look at, what was the effect and what kind of things can I do with that? The other thing is as we looked at the various different things, we looked at, well, what happens with DPI? What happens when we go from a bidirectional pass to a cross pass to a cross pass that's tilted at 45? And what are the effects in the material? And what could we do with that? So we went through yesterday and the day before and did a bunch of burns. This is the 35-watt side. This is the 70-watt side. And then another important area is the destructive testing. And it was quite important because when you went to 50 watts in 70-watt mode, you actually caught the wood on fire, even with all the advanced airflow. When we started running cross mode, on the, we got through the horizontal okay, but the minute we started going vertical, we started catching fire again. You can see all the carbon coming off. And of course, the enclosure was incredibly smoky. Then we started reducing the power, and we went from 40 to 30. And we then started seeing, oh, I'm getting an edge. I still have lots of flame and backflash and backblast all over the material, but at least we are now starting to determine a safe operating area. And this is important. My lasers are highly modified. My enclosures have been purposefully engineered to ensure that we carry the maximum number of material from the debris out the exhaust stack so it doesn't actually coat the laser. But with your stock lasers, you need to do this kind of testing, and you need to be watching it when you do it so that you can safely operate your laser. So again, what we found with this material, which is probably oak, and it's 28 years old, so it's been around for a while. It's had a lot of heat and humidity cycles. Originally, I thought I was going to have to use 70-watt mode. As it turned out, because of all the experimentation, basically bracketing, DPI, changing power levels to kind of at first go 20, 30, 40 to kind of see, okay, where's the best place to run? As it turns out, with this material, it's right in the middle. So everything up here was done at 35% power in 70-watt mode. And then, of course, we started experimenting with the patterns. Again, we repeated the experiments in 35-watt mode, and we actually got a cleaner result out of that because of the smaller beam size. And we also got some more interesting patterning, which was kind of unexpected. I expected to see grain, but I didn't really expect to see this kind of patterning. So when you're thinking about lasers, some of the most important things to think about is, what does the laser see? So we have our laser, and it's sending effectively a cone. It looks like this, and this is the primary focal point. And all these examples measured from the tip of the cone, because that's a convenient reference point to the surface, is 15 millimeters. Now, if you look at the light burn move sheet, you'll see that if you do get, and it reads back, where the laser is, it's going to show you 14. And the reason is the computer counts from 0 to 14. So that's actually 15 in terms of absolute distance. So we've got the laser, we got our cone there. The actual focal point is +5. It's actually 20. And when it's at 15, and this is what autofocus does, and we did everything with autofocus, so we had a very consistent mechanism for determining distance of focal point on the material. What we have the option of doing is we can go -5, which is basically going to give us 20 millimeters. 15 is autofocus. And then that gives us 15 to 1 millimeter range in terms of changing the depth of Z depending on what we're doing. So your total focal range here is about 20. Now you can move the head up and down for things that are farther and closer to the focal point, but you have to be very careful not to crash the tip of the laser into the material if you're doing that. When you look at how the atom stack gantry works, is there's a little gauge on the side, and there's 5 millimeters between here and here, that when you set it, you have the nose of the laser on the top of your honeycomb. Usually put a little 1 mil card in there so it's consistent. And then you adjust 5 millimeters right here. That's the optimal place to tighten your set screws down and set your laser up. That way, in all the examples that you've seen, this is the reference point for all of the autofocusing and focusing that you're doing on the workpiece. So when we're thinking about this and applying it to laser milling, we have a piece of work that we have, and we're basically trying to cut a pocket. Now there's some things to think about. How deep should you go? Well, the problem is we have a kind of a flattened sphere, kind of looks like an American NFL football, that when the beam comes out on the work, it's basically taking that sphere and moving it in whatever direction. And it has a hot ball of plasma that is vaporizing with very high and very fast temperature buildup, basically turning, in this case, the cellulose of the wood and its fibers into vapors and gases. And that's where all your smoke is coming from. So what the beam is pointed at when you're at autofocus is actually below the surface of the material. Unless you set it at 20, and which means you autofocus and then you use the Z command to go in and bring the focus farther up. So it's sitting at the surface, which would be 20, this being 15 here. This is how we're adjusting the depth. Now, in actual practice, you're going to autofocus. You're going to use very, very small increments of Z per pass to start going in and putting a pattern. First thing you're doing is burning the paint and shellac off in this particular case. The next thing you're doing is you're starting to mill. And typically the Z increment is going to be 0.5 millimeters. Now, if you want really fine resolution and minimum charring, you might go as low as 0.25 or even 0.125. What that does is it says I'm making much smaller vertical increments. And bear in mind, every pass takes time, so you have to think about that. But depending on what your requirement is for deviation in surface, and again, when you're doing woods, it's very variable because of the grains. The grains tend to not burn nearly as well, and so you're going to see a bottom that looks like this. So you'll have the top of those, and you'll have the bottoms of the troughs to think about. This is deviation from the average surface level that you want. And the smaller you make this, and using lower powers, you're not burning as big a ball. You're changing the size of the plasma ball that you're doing the milling with. If you have the time, you can refine that so you get a fairly flat surface. Now, for practical inlays, you're basically looking at the highest average surface, and you're going to put glue or filler in the bottom. So those are some things that you need to think about. So as we continue our discussion, we're looking at putting pockets in scrap wood. And so we're now starting to peel the onion a little bit. We've talked a little bit about the cone of focus that comes from a laser. One of the other things to think about in a laser is how the diodes are set up. So what you have is typically in a 14 diode laser, and it would be similar for anything that uses more than one diode, is we have a bunch of rectangular diodes. And the reason why they're rectangular is that is the least expensive way to manufacture them. Now, there are differences between lasers. If you look at a CO2 laser, because that's a gas laser, you actually get a circular pattern or a circular beam. And so circular beams are quite useful, but you're only going to find that in gas lasers. You're not going to find that in the other variants. So when we look here, this is what a 14 diode laser looks like. If you take and put a a concave lens in front of this and shine it up on a wall, you'll actually see the individual diodes. You'll see 14 total, 7 in each column, and 2 per row. Now, this is a function of what we call the COS module. And a COS module is a single substrate that has a whole bunch of diodes that have been deposited on a piece of silicon. And then at some point, there's a lens mirror combination that takes each of the beams, which has a particular angle from the substrate, this part right here, and they focus, in the case of the current lasers, this set of beam is focusing one half, and this set of beams is focused on the other half. So the end result beam is the two halves. So when you're in 35 watt mode, you have this half on. When you're in 70 watt mode, you have both sides on. And so you go either one half or times two, depending on your point of reference, the beam size. Now, one of the questions that's obvious to ask is, why didn't the manufacturers simply superimpose everything on the same single beam point? And in fact, they can. It's very simple mechanics and very simple optics. You don't even need to change the lenses. You just slightly tilt the mirrors so all the images focus in one spot. Now, if they made them that way, we would have the ability to have a full 70 watts in the same space that we would have 35 watts. And this gives us much better resolution when we're coming back over here trying to do laser milling. So this is today's current lasers. I have provided some feedback to several vendors about, well, why are we doing this dumb thing? You know, we could be doing this. We could have had a V8. But again, this impacts when we're doing milling, because when we look at the mill from the top, let's just say we have a little square here. And of course, you can circular mill too. I'm just using square for an example. What we're really doing is running passes like this across an irregular surface, and we are ablating or vaporizing or turning to ash the soft tissues and the fibers. And of course, those have very different mechanical and thermal characteristics in terms of how they burn and vaporize. So if you have a piece of MDF instead of a piece of hardwood, hardwood has very, very distinct structure in all of the grain. So you'll see a heavy fiber structure, and then there'll be a lot of soft tissue surrounding it, which is primarily cellulose. So the cellulose will burn out quite deeply. The fibrous stuff is much more resistant to burning. But there's a couple different ways to look at that. What effect are you going after? If you would like a really neat, you like the grain, it's an artistic thing, you can basically do the examples we've done here, and you could actually simply show the grain inside a cutout. And effectively, you're building a 3D image. But you are going to have the grain showing distinctly, and probably even up to 2 or 3 mils difference in height in the pocket that you're working with. But from an artistic perspective, that gives you a whole nother range of things to do. If we look at the work that Sky Ewing does, and she does beautiful work, she is really brilliant about leveraging grain. To her, it's not a problem, it's an artistic opportunity. And that's one of the reasons why I really enjoy watching all her webcasts, because she has taken a lemon and turned it into, you know, a really nice vodka mixed lemonade drink. which she does, just beautifully. So it really depends on what the use case is and what your direction is in terms of what end product do you want, in terms of how you might approach getting the various effects. And of course, milling is one of the options we have for tailoring our base materials for the either artwork or the product you're building. Now, another thing about milling is, let's think about time. So if we're just doing a bi-die pass, at least in the diode lasers and the ones that I'm currently using, that's usually the quickest way to mill a surface down. The problem with it is you're either going against the grain or you're going with the grain, depending on whether you do an X or a Y pass. And if you're doing a vertical pass, you're going to see all the grain. If you do a horizontal pass, you're going to get you're going to be cutting the tops off of the heavy fibers and maybe not deleting as much of the cellulose surrounding them. So it's an option. And from a time perspective, bidirectional makes a pass this way and that way. That's one pass. And it continues from top, bottom, or side, passing as you're milling out your materials. So typically on a 50 by 50 mil square, which is what we're using in the examples, running at 10,000, 35, the runtime is about 15 minutes. The minute you start doing a cross pass, which means I'm now going and adding this, so now I'm going back, forth, up, and down for one pass. So it's basically, it's moving the laser head across the materials 4 times when you do a cross versus a bidirectional. Then you look at, okay, so how deep am I getting with a single pass? And so the question you're asking is, if I do one pass, where is this? This is the highest average. This is the lowest average. How much variation am I getting between high and low? And realistically, if I'm doing an inset or an inlay, I'm going to probably use the highest one and just fill the rest with glue. So then the question becomes, okay, on this material, how much power can I run without creating a flame problem so I can mill most efficiently? What's the right speed? Should I be making changes in focus? Should I be doing a cross, a bi-die, or a 45 angle cross in order to surface the material I'm with? And again, if we're using MDF, you're going to see almost no variation between highest and lowest average levels. So MDF, if you want to do inlays, is a really excellent material to use for that because it's dimensionally stable. Or as another person put it, it's all glue. But it's very fine grained as opposed to the oak material that we're looking at, which has very, very strong grains. In fact, it was fascinating as the pockets got deeper and deeper to see the changes that each pass would make. And from an artistic perspective, you could take the number of passes. Once you've got the first layer off, you can start looking at the grain and saying, okay, I'm going to do it this way, then I'm going to try it this way. So maybe I started out with a bi-die to kind of get the junk off the surface. Maybe I ran 4 passes of that. Now I've exposed the grain, and now I'm going to take a mix of cross with 0 angle and cross with 45 angle, and I'm going to vary my speed a little bit, maybe my power a little bit, so that I'm working just under the threshold of setting off my flame detector. Now, the other thing to think about is the amount of debris and smoke you're going to generate. If you have an open frame laser, your room's going to be filled with smoke in a very short period of time. It's the same thing as setting a fire to your house. And of course, you don't want to breathe that. So if you're going to do this with an open frame, make sure you're at least in a garage with an open door and you got a fan blowing across so that you're breathing as little of this as possible. And you really should wear a filter mask. If you have an enclosure, remember today's enclosures, and the K3 from iCure is a perfect example for a large frame laser. It's got a little itty bitty fan off in one corner. It doesn't have any directed intake airflow. It has no intake coming from the outside into the enclosure. So it's running at about 30 to 40% the effective CFM that the small fan could do if it had an intake port. And the exhaust port's pretty small. And when you see the volume of the enclosure compared to the size of the exhaust port, it's clearly very undersized. And the problem with a small 100 or 120 millimeter fan, especially muffin fans, best case, you might get one that's 100 CFM, maybe 120 if you run it at real high speed. But you're not getting enough air across the chassis. And the problem is you're going to get a lot more smoke. You're going to have a lot more problems with your flame detectors setting off, and you're going to get tons and tons of buildup both on your laser from the parasitic flow and on your workpiece. So a properly engineered enclosure and some of the mods we've talked about earlier to the laser itself with filtering and tilt angle all make a difference in terms of how well you do trying to cut in a pocket like this. This is probably the most difficult thing you can do with a laser. So it's very material dependent. If it's a grainy material like a hardwood, it definitely requires some thinking and some testing to see, how do I want to orient the grain? Do I want to run across? Do I want to run just a regular zero angle cross? Do I want to run a bidirectional pass? How small of increment do I want to use in Z? Because the best way to level these out is lots of really, really small passes. If you think in 3D printer terminology, 3D printers do the same thing except for they're additive, they're adding layers. And each of these layers is referred to as a slice. And all it's doing is saying, okay, I'm going to generate a G code for this particular slice, then I'm going to do another one and so on. And believe it or not, this same technology, if it was integrated into Lightburn, for example, could be used to add a tremendous level of control in the Z-axis, which doesn't exist right now, which would allow us to be much more refined in terms of doing things like this. Also, if you're working with paints, well, think about what you're doing. If you have a tile, and then I have 4 different layers of paint on here, maybe some metallic on top. Well, what we're doing is in the Z-axis, this is where power, speed, and depth allows us to selectively change colors by increasing the Z. If you use Z, you get the best result. And when you're doing a test pattern, you want to basically build a little matrix of squares, and you want to use something fairly large so you can really see the result, which is the reason why I went to 50 mil square as opposed to the normal test squares, which are typically 5 mil or smaller. The problem with those is, A, there's a lot of heat buildup in a small area, so you get a distorted view of what's actually going on. And you can't really see what the average effect is over, say, a 50 mil square area. So by having that larger test square, I can see more details. And when I'm doing very small increments of Z or very fine increments of power, for example, this is allowing me to selectively burn down in the same way that we're doing the milling of scrap wood, we're now doing milling of paint on top of ceramic or glass. So the same basic principles apply. Now, the other thing to think about is, how do diode lasers work? Well, most diode lasers work at a frequency of 10 kilohertz. And so when you're running an M4 mode, which is constant power mode, there's two things that determine the optical power. So if we look at this square wave, which is the pulses going down to the driver transistor that's switching the diode off and on, there's a couple of things that are variables. The first thing is, if we look at the square wave, and let's blow this up so it's a little easier to see. So we have a cycle. We have a high and a low. Now, when you're doing pulse width modulation, you're changing the length within the cycle of the on time. And so what's happening on the workpiece is it starts at room temperature, then spikes up very quickly to maximum temperature, which could be 5,000 or 6,000 degrees centigrade. That lasts for as long as the pulse is high. And when it drops, then of course it starts to cool. So it looks like this. And if you look at it over thousands of pulses, basically what you're going to see is heat rise in the material that looks like that. So the longer you're lasing, you're incrementally, every time you turn it off and on, you're not getting rid of all the heat. So you're going to see heat buildup in the material. And you'll notice that when we start getting to edges and so on, the heat buildup, because of the angles and so on, is more intense at the edges than it is in the center. If you're using metals, one of the effects that's quite pleasing to do from an artistic perspective is, what you're doing is actually hardening or annealing the metal. And you're doing that by heating it up and then controlling the cooling. So in the metals, it gets hot real quick, it's hot for a certain amount of time, and depending on how quickly it cools, helps determine the color. And if you want to experiment with just a butane torch and a piece of steel or a piece of stainless steel, stainless being much more sensitive and giving you much wider color variation, you're basically watching tempering. And what it's doing is the heat is reorganizing the crystalline structure. And when you look at this in daylight, you're going to see, because daylight's a very broad spectrum of color, this allows you to see different colors in the material. And effectively, you're looking at differences in hardness from a function of the rate of time that the beam is on, the amount of surface area that the beam is heating to the maximum temperature. And if you just take and do a quick pulse, you'll actually see a almost circular pattern from it. And you'll see at the hottest point in the center, it'll be one color, and then you see a range of colors like a rainbow that are going out in a circular manner from the center of the beam. So as we look at different materials and we look at milling, the lessons that we've learned from the scrap wood experiment also apply to other materials. And now that we understand a little bit more about how the laser fires, and we understand the heat buildup, the heat decay, the cumulative heat, and this cumulative heat is also reflected in the heat sink in the laser. And it's one of the reasons why it's inadvisable to run lasers at over 80%, particularly in high power mode, because you're really pushing what's called the safe operating layer of the laser. If this is the temperature buildup in your laser, of course, time determines part of that, but the heat sink, if you're running 100% power, probably limits right there. And so all the stuff above the red line to the black line, that is basically outside the safe operating area, which is down here. And what you're doing is you're raising your laser very rapidly. The lasers are extremely sensitive to dirt in the optical path, but also reflected optics back to the diodes. So your diffraction grating, which Atom Stack builds the best one I've found so far, which is the output filter. It's not actually a lens because it's flat. It doesn't have any change to the optics from a focus perspective. It's constantly getting hot and cold spots generated, and over time the crystalline structure breaks down because you're going outside of its safe operating temperature as well. When you add debris, which oddly enough comes in through your air assist system because none of them are filtered, that atmospheric dust or dirt is coating the lenses, and any backflash or any back debris bouncing off the media going straight up the laser tube is basically coating and creating a hot spot. So again, this curve now starts moving down because you have less and less ability to get light through the output filter, and it more and more going back into the diode stack and heating it. The same thing is happening on the materials. We hear a lot of people talk about, well, my laser isn't doing real well. I can't seem to cut anything and so on. Well, it's usually because you haven't been cleaning it. The more complicated part, particularly when you're doing milling, because milling is extremely smoky, is the fact that unmodified lasers are sucking all that filth and depositing it inside the laser enclosure, and it's extremely difficult. It takes hours of very carefully wiping down with solvents to clean the inside of the laser. And there are areas that unless you totally disassemble the laser, which is not recommended because part of the heat sink of the circuit board is actually the outer case. And so if you take the circuit board out to clean it, you have to put heatsink grease back in, which is more complicated than most people want to go. So again, when we're doing this milling, we have to be ever mindful of the cost to the life cycle of the laser, the circuit board, and so on. The other thing, of course, we talked about in one of the other discussions was the fact that it's also coating your connectors and all your mechanics. So when you're doing milling, whether it's wood, whether it's plexiglass, which is something I'm going to try here in the next few days. I've been doing engraving in plexiglass, certain plexes with the correct colors that are 180 degrees opposite of blue, which is orange-red, do actually cut and engrave just fine. The minute you go board in about 15 degrees either direction, of course, it gets less and less effective. So the myth that you can't do translucent acrylic is not entirely true. So I will do some experiments in the next week or so with, I'm probably going to use 6 mil acrylic, mainly because the thinner the stuff may fracture when we're trying to mill it. So that's part of the milling experiment that will continue in later phases to get a better idea of the fitness of cast and extruded acrylic as compared to hardwoods. Now, the other piece that bears some discussion is plywoods. So a lot of the cheap dollar store, what I think is basswood, although they don't really say in the packaging, is basically 2 layers of wood. Just 2 pieces of veneer that have been glued back to back, which effectively makes a 3-layer board, sort of. Basically, there's the glue in the middle. And the interesting thing is it lays really well when I'm trying to do an image or a drawing. But when you try to cut it, You have to turn the power up fairly significantly to get through this thin, um, almost plywood, because of the glue layer in the center. Glue does not burn very well. It also leaves lots of ash and smoke compared to the facing material, which are the two outer layers. So again, you might want to mill that as well. But the problem is, if you're below 3 mils, milling's not real practical unless you're just using foil, or you're making a little pocket to do alcohol, ink, or acrylic paints, where you go through and you do a very shallow mill. Then you go through and put an opaque white and let that dry for 24 hours, which is sealing all the material. And then you come back and you hand paint on top of that, which gives you a nice bright color. So those are some of the tricks you can play with. You can also do the same thing with black, but that's only good on darker colors. You don't really want to use black with lighter colors. Again, it's an artistic thing, and in the art world, it's whatever sells. So that's a good thing to experiment. And it's another example of how doing milling with the laser can help you with other surface treatments. Another thing to think about is raw wood, which has been untreated. And there's a couple categories of raw wood. There's raw wood that is green, it's just been cut, hasn't been dried. What it's going to be full of is lots of tar and pitch. And so the tar and pitch, of course, will burn. So you have to adjust your speed, your Z. You've got to adjust the power levels to accommodate the difference between a wood that is green, which has just been cut and milled, and a piece of wood that's 30 years old, which has gone through thousands of heating and drying humidity cycles. And so the material has stabilized. Because when you're thinking about wood, when it's first cut, it's still very flexible and pliant. Wood that is aged several years, for example, basically is turned into a fossil. You're basically peeling layers off a fossil. So the bones of the fossil is the heavy fibrous tissues, which we refer to as grain, and the stuff in between is the soft tissue. And the soft tissue is now hardened and crystallized, basically the way diatoms are from the sea creatures that they come from. You now are dealing with fossilized materials. Now, another thing that you might put a pocket in is a piece of rock or slate or granite or marble. In each of those, you would go through a similar process to determine, well, how smooth of a base surface can I make? How can I reduce the average top and bottom depths so I get a smoother surface for the artistic effect or the inlays that I want to put in? So again, this basic discussion does talk about how you can apply this across multiple border cases. A border case is a use case where wood was the core use case, because that's what we were primarily investigating. Then the question is, what can we do with a case that's similar to it, which becomes a border case? And can the same settings or process be used to create a similar result, in this case, milling a pocket? So as we think about all these elements, now you understand why folks like Sky and Dave Clackerly and Steve and so on do a lot of testing, and they do a lot of process validation. The technical term for that is characterization of materials, or material testing. And effectively what you're doing here is the same process you use in a beta test, except for your beta testing materials, you could combine a beta test of beta testing a laser using the beta test materials that you've already tested. Those become use cases for the beta test to look at how well the laser does. And if you're comparing different lasers, because you've characterized the materials, you're now taking a known set of material characteristics and using those as a set of use cases for beta testing across a mix of lasers. So you can see how each laser type does in terms of, for example, doing a pocket. You remember, a pocket is just like doing an engrave, except for it's deep. It has more Z. So regardless of whether you're doing a graphical image, because it's creating micro pockets, lasers chip things away or they ablate them, depending on the material type. When you get into crystalline structures like glasses, mirrors, and so on, or steels or other metals, you're basically ablating and you're chipping. And the smoother the material, and depending on the chemical and physical characteristics, you'll get a mix of heating, and heating basically right here causes a fracture. And so when you're going through and doing your glass, for example, you of course have to put a masking surface on. And then what you're doing is the masking surface, which is typically black, tempera, or you could just use spray paint, but it's a pain to clean up, is basically doing a little dot that basically is representative of the plasma ball and the shape of the output beam. And it's going through and going blast, 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 blast. You get the heating and the cooling effect. And what happens is the rapid heating and the rapid cooling is basically causing the glass or, hard rock surface, things like that, similar materials, to fracture off a small piece. And this is the reason why, again, good enclosure design, good filtering, and if you're using an open gantry laser, again, this is dangerous stuff because you're creating a whole bunch of toxic materials that you and your pets are going to breathe. And that's because of the rapid heating. It goes from a room temperature state to plus 5,000 degrees centigrade. And this is releasing a whole bunch of volatiles, gaseous things, as well as hot debris everywhere. So again, as we're going through the milling example, we now are starting to gain an understanding of, okay, what else can I do with this? How would this apply to that? We have a consistent process now. We've kind of, at least for the hardwood example, have sat down and characterized, okay, where does it actually work? What's the bounding box of conditions that we set and processes that we use that allow us to do the pocket we want? And now if we're going to do something similar on a different material, we have a process we can use to quickly arrive through the experimental process or the beta process to determine what else works. And so that's one of the more valuable pieces of this very silly little experiment. The other part of this experiment was to say, okay, this is old recycled wood that normally would just be put in a dumpster and thrown away. Because of the cost of materials rising, the question is, oh, well, I got a whole garage full of this. Can I use any of it? And so the milling example is actually a good way to characterize scrap wood or scrap materials. Because as the cost of goods increase because of all the nonsense in the global economy, using recycled materials becomes more and more cost effective. And when you look at a recycled material versus a new material, you're going to go through a research phase like this to figure out what you can do. Then you have to pay attention to the time that you're working to get the materials to a usable state. And after you've figured that out, you look at how many minutes does it take, how much effort do I have to do it? Do I need any other materials like solvents or so on to get the result I need? Then you compare that to the difference in price of the new material previously and the new material today, and you look at the difference between that, and that'll determine whether the scrap wood is more cost effective in terms of your end product, the overall cost, than the new material. So those are kind of the business operational aspects of this same piece of research that you can extend to. So now we've gone through multiple dimensions. We've talked about the art, we've talked about general reuse of materials, using the milling test to kind of help us sort through what works and what doesn't. We've talked about some techniques using the z-axis and power and beam width and other techniques to help us get closer to getting a more optimal milling. We've learned a lot about our laser's capability in terms of how the laser works, particularly for diode lasers. Other lasers will work similar. You'll have a different matrix of results. In lasers that have the ability to change frequency, that actually becomes more important than power does. So that's where there's a slight difference, and all you're doing is adjusting one or two more variables over the same basic process to see what kind of results you can do. So hopefully this has been a useful discussion. I wanted to peel the layers of the onion back a little bit to help you see opportunities to do more things with your laser, help ensure your safety, help ensure the longevity of your laser, different things you can do with materials and how you can take a core use case, apply it to a boundary case of something similar, and reuse a lot of the settings and the process. This, of course, helping you gain and document what you've been working on experimentally when you're doing your testing of your materials to help you make more effective use of time and materials and save expense anywhere you can by going outside the normal box of let's just put it in and see what it does, and actually taking time to do a programmed series of experiments to see what is the range of those things. So hopefully this has been useful. As always, I greatly appreciate other people's opinions. They have insights that I don't have, and as I collect them over time on the YouTube channel, I also post these on Atom Stack, the official group, every time I make one, that we can collect feedback to help refine the experiments that we're doing so that we may build more precise data sets that hopefully will be of practical use for the laser community. Thank you everyone for watching. Cloudfather out.